Okay, here I would like to talk about the stereochemistry of the hydrohalogenation. Now, one of the things you'll notice is that when you take one pentene and you treat this with hydrochloric acid, you can get the two possible stereoisomers. Okay, you can get the S isomer or you can get the R isomer. And these are formed in equal amounts. We call this racemic. Okay, a 50-50 mixture of enantiomers. Now, because you get a 50-50 mixture of enantiomers, we say that the reaction is not stereospecific. Recall that the same thing happens in the SN1 reaction. Okay? So how does this occur? What's going on there? Okay? Now, when you draw the reaction, in the first step, what we have is hydrogen chloride here engaging our alkene, and there's a protonation event to give you a carbocation. Okay? And this carbocation then attacks or reacts with chloride, and we need to think carefully about the structure of this carbocation. The carbocation is an sp2 hybridized creature with a, in this case, a propyl group here, a methyl group, and a hydrogen. And this is a trigonal planar flat molecule. Okay? You know, you might shade the orbitals differently, red and blue, if you have really nice crayons or something. And it's a positive charge, right? And the chloride can attack from the top face or the bottom face, giving you the two different enantiomers. And it's a 50-50 chance, okay? So we can come from the top face, or we could come from the bottom face, okay? Now, this equation isn't balanced. You could say 2 moles of this forms 1 mole of that and 1 mole of that, but we're not really interested in balancing these chemical equations. But don't fall into the mental trap that one molecule is somehow changing into 2 molecules. Okay, that's not what we're talking about. We're just saying that half the reaction mixture can provide the S or the R through a 50-50 chance of attack on either side of this flat planar carbocation intermediate. And it's like flipping a coin. It has an equal chance of landing on heads or tails. All right? So let's do some practice problems here. On problem 9.6, it says predict the products for each of the following reactions. In some cases, the reaction produces a new chirality center, while in other cases, no new chirality center is formed. Consider that when drawing the products. Okay, so let's go ahead and do this. All right. Now, if you're kind of a beginning student and struggling a bit with you know, stereochemistry and these reactions and all of the plethora of information here, take it stepwise, okay? Step 1, draw your carbons, draw any hydrogens, figure out where the hydrogen goes and where the bromine goes, okay? So hydrogen goes here, bromine goes here, okay? So in the product then, just draw a line drawing. Don't draw any wedges and dashes yet, okay? So draw all the carbon framework without the pi bond, then add bromine and hydrogen, okay? Then carefully consider if there's a stereogenic center. This one here is a stereogenic center because it contains 4 groups. It contains ethyl, it contains propyl, it contains bromine, it contains a methyl group. Okay, that line is just a methyl group. So what you want to do now is expand this and illustrate the stereochemistry. So you want to draw the bromine on a wedge, the methyl group on a dash, and then you want to draw the other possibility, bromine on a dash and methyl on a wedge. And those are going to be the 2 products that you form. That's question A. Let's do B. 9.6b, we've got HCl. Okay. Take it stepwise. Step 1, draw the carbons of your alkene. Step 2, draw any missing hydrogens. Step 3, the rich get richer. So identify which carbon is going to pick up the hydrogen, which carbon is going to pick up the halogen. Okay. Step 4, draw the carbon framework, just the sigma bonds. Step 5, draw in a hydrogen, draw in the halogen. Step 6, identify if you have any stereogenic centers. Now look at this carefully, okay? This guy here has a propyl group, a propyl group, a methyl group, and a chlorine. Since it does not have 4 different groups attached to that carbon, it is not a stereogenic center. We can just draw a line drawing to illustrate the product. There's only one product here, and it's not chiral. Let's do problem C. The starting material is a cycloalkene. Okay. And we're adding HBr to this. Okay. So again, step 1, draw your carbons. Step 2, draw any missing hydrogens. Step 3, identify the richer get rich. That's where the hydrogen goes. And the bromine's going to go over here. All right. Next step, sketch out the sigma framework only. That means only the single bonds in this molecule. And then add in your atoms that you've indicated where they go. So bromine's going to go here. Hydrogen's going to go here. And then we want to identify if there's any stereogenic centers. Okay. Let's look at this carbon right here. So we have a bromine group attached to it. We have an ethyl group attached to it. Okay. We have a CH2 group right there. Okay. And we have a carbon with 2 methyl groups. Okay. So it does have 4 groups attached to it. So therefore, we need to draw both the wedge and dash, or the R and the S isomers for this molecule. So the bromine could be on a wedge, the ethyl group could be on a dash, or the other way around. Okay, so we'll draw the ethyl group on a wedge. Okay, and so those are the 2 products that are formed in equal amounts. Let's do problem D. Problem D, 9.6D. We have a cycloalkene. Okay. How would we number this? How would we name this? This would be 1,4,4 trimethyl cyclopentene. Cyclo because we have a ring, and pentene is always assumed to be carbon 1 if you have a ring, okay? So we don't need to say 1 cyclopentene. In any case, this reacts with HI, and we're supposed to figure out and draw the products, right? So step 1, draw your carbons. Step 2, draw any missing hydrogens. Step 3, identify the richer, right? And figure out where does the hydrogen go. The one with more hydrogens gets the hydrogen. And this one's going to get the iodine. And now we are going to draw the products here, just as a simple line drawing first, okay? Don't try to draw any stereochemistry yet. So once again, you sketch out the whole single bonds all in your molecule first. Then you add the iodine, okay? And you add the hydrogen, okay? And then you identify any stereogenic centers. So again, this molecule does not have a plane of symmetry through it because you have two methyl groups on one side and just CH2s on the other. So it's asymmetrical, it's chiral. So because of that fact, we need to draw both products. So those methyl groups, you don't need to use wedges or dashes on that because there's just two methyl groups. But for this, we do need to show stereochemistry. So the methyl group could be on a wedge, the iodine could be on a dash, and the other way around. Okay, so that's going to be the products there. Let's do 9.6e. Okay, we've got this molecule here, HCl. So follow my procedure again. Draw the C's, draw the H's. Carefully consider where your hydrogen's going to go, where your halogen's going to go. Draw only the single bonds out. Then add in the atoms that you're adding, the H and the Cl. And then determine if there's a stereogenic center. Okay? Now, in this case, be careful. That is a CH3 group. Okay? And this is a CH3 group. So, because this molecule does not have a stereogenic center, we just draw lines to indicate the product. Okay? Let's do 9.6f, and this is a very good question. This is the most advanced one here. A lot of students get to this point and they kind of give up. Let me show you. You draw the C's, you draw the H's, and then we have to decide, oh, the richer get rich, but they're both equal. So what do we do here? I don't know. And students sometimes get stuck. Now, this molecule is symmetrical, okay, in a way, because if you number it from left to right, or you number it from right to left, you're going to get the alkene at carbon 2 no matter what. So basically, you're only going to form one molecule, one product, I'm sorry. You can add the hydrogen on the left and the chlorine on the right, which is identical, equivalent to doing it the other way. Okay? If you do it this way or this way, you still get 2-chlorobutane, all right? And 2-chlorobutane is a stereogenic center, so at the carbon 2, so we need to draw that in two possible ways. Drawing the hydrogen is optional here, okay? That's always optional. So those are the two products from this reaction. Okay. The book talks about carbocation rearrangements, and we've been over this enough to know what's going to happen. So if you have something like this, will this give rearrangement or not? So you need to think through this stepwise. If you treat this with hydrochloric acid, will this result in rearrangement? So you need to think through the mechanism. You first are going to protonate your alkene to give you a secondary carbocation, okay? And remember how we decided if there's going to be a rearrangement. If you have a more substituted carbon nearby, right next to it, it will rearrange. This is a tertiary carbon. Okay, we say it's tertiary because this carbon's connected to 3 carbons. Okay, but this carbocation is only secondary, so the answer is yes, it will rearrange. Okay. Now, some instructors and professors will ask you to write out the whole curved air reaction mechanism with the very intricate rearrangements. So be careful what you're studying. I personally don't care if you're able to draw all those rearrangements, just to be able to identify if there's a rearrangement or not. Okay? So that's a bit about the hydrohalogenation. Let's stop there.